I'm doing this again because if this is flat, you're folding each of these outside pieces in so they line up on that line. Okay. If you have a crummy scissors, you can borrow my blue one, just make sure. Okay, when you're cutting, please do not obviously cut all the way through. You're just cutting on the dashed lines so that you can open a flap for y-intercept. We're actually not going to do slant asymptotes, but it's still on there. Okay, so then you have these little flaps that open up. Okay, so what we're going to talk about is everything. I'm not going to even talk about slant asymptotes. Slant asymptotes are, you know how when there's no horizontal one, sometimes then it goes kind of off into the distance on a slant. I'll talk about them in pre-calc. All right, reduced form. First of all, I'm going to give you an example of something that's in original form, factored form, and then reduced form. And so for our original form, on the top, so this is under reduced form. Under original form, we're going to write f of x equals x squared, x squared minus 3x minus 10, and on the bottom, x squared minus 25. Yep, x squared minus 3x minus 10. Okay, so if I did give you something that was like this, we don't know anything about holes or asymptotes or x-intercepts, so you would need to factor it. At your tables, can you factor x squared minus 3x minus 10, please? At your tables, can you find the factors of x squared minus 3x minus 10? Talk about it. At your tables, you're supposed to be factoring x squared minus 3x minus 10. X minus 5, x plus 2, yes? Is that what I'm hearing? Okay, on the bottom, how would you factor x squared minus 25? 5 and negative 5, so x plus 5, x minus 5. Okay. So that would be its factored form. Okay, what would be its reduced form then? Reduced form means you're going to cancel something out of top and bottom. Can't you cancel the x minus 5 on top and bottom? So we would be left with x plus 2 over x plus 5. What does that make 5 on the graph then? A hole. If it's on top and bottom, it's a hole. x, because 5, okay. All right. So, as I'm going through, if I ask you, for some of these, I'm going to use this example then, okay? Which is a little not representative of everything because this is one with the degrees, where the degrees are the same. Okay. All right. Removable discontinuities, those are also called holes. So in this one, discontinuities, if so, where do they exist? So the holes are going to happen when there is the same factor on top and bottom. And that, it's what makes the factor 0. You remember that? They're the root of the factor. So the root of that factor, what makes it 0 is a hole. Some people like to remember it as it's the opposite then of the factor. So using my example from above, where would the hole occur? X equals positive 5, because that's what would make this 0 and it's on top and bottom. Okay. How about vertical asymptotes? You're going to find your vertical asymptotes from your reduced form. We're just kind of using this side here. So in my, after I get rid of the hole, look at my reduced form. And anything that's remaining in the denominator set equal to 0. So what's x plus 5 equals 0, which would mean, where is the vertical asymptote? At x equals negative 5. Okay, x-intercepts, you also get your intersect. This should actually find your x-intercepts from your, this should also be your, would you cross out factored? This should be your reduced form as well, because the whole is not an x-intercept. So once you have your reduced form, you set any factors in the numerator equal to 0. So go up to the top and look at my reduced form. What's on the top? X plus 2. That's after it's reduced. I set x plus 2 equal to 0. I subtract 2 from both sides. There is an x-intercept at x equals negative 2. Okay. So this is just solidifying like our exploration last week. Is this stuff coming back to you? Some of you, maybe, I hope. Okay. Now, something that we did not talk about on your specific explorations, but is always true in any scenario. If you want to find a y-intercept, the y-intercept is always when x is 0 in the graph, or f of 0. In this case, f of 0, if I plugged it in, and by the way, you can plug it in from any of the forms that you want. It doesn't matter. Just realize if you plug it in like factored form, that what operation is between the parentheses? Multiplication, so it would be like negative 5 times 2. Okay. But you can plug it in the reduced form if you want, because essentially these would cancel anyways. if you plugged it in the top, you'd get 0 plus 2. What's 0 plus 2? 2. And then what's 0 plus 5? 5. So 2/5 or 0.4, that means it would cross at 0.4 or 2/5. Okay. Horizontal asymptotes. You're going to find the degree of the numerator and the denominator, and you're going to compare them. In the one example that I gave you, is this numerator less than denominator, numerator equal to denominator, or numerator greater than denominator? Which one is this? Look at the numerator. What's the degree? Two. It's 2. Degree was 2. They're the same, yes? If numerator equals denominator, y equals the ratio of the coefficients of the leading terms. What's the leading term? 1, 1. 1 divided by 1 is 1. This one would have a horizontal asymptote of y equals 1. Okay, so that's how this chart works. If the numerator is a degree less than the denominator, you don't have to do any work. It's just 0. And if the numerator is greater than the denominator, there is no horizontal asymptotes, but you must check for slant asymptotes. No, we're not going to do that. Just for us, just know that there is no horizontal asymptote there. So you can just cross off where it says must check for slant asymptotes. And then we're going to just put an X on the slant asymptotes. We're not going to look for those. Okay. End behavior. What you need to know about end behavior is it is the same as the horizontal asymptote. So the function is going to approach the same value as horizontal asymptote. So if I asked for the end behavior of the function in my example, because the horizontal asymptote was 1, its end behavior would also be 1. And that means as x goes to infinity and y goes to infinity, the function's going to approach a fixed value of 1. Okay? So end behavior in rational functions is the same as its horizontal asymptote. Okay.